So the PDF is like the probability of any given point being chosen, right?
Not quite, because the probability of any point is actually zero, right? But it's the relative probability. Yeah.
Okay. And the second is talking about it over a range specifically.
Over the range of negative infinity to that point, and that is finite. Right. So this is like kind of when you want to actually sample things or get probabilities. Cool. So today we're going to talk about 3D graphics. Lots and lots of undergrads take a whole course on this stuff, but we're just going to hit kind of the highlights. So there's a few core concepts that make up 3D graphics. We're going to talk about geometry, transforms, talk a little bit about cameras, and then shading. These are basically the things you need to render 3D graphics. There's a whole bunch of different ways you might represent or work with any of these, but you're going to have to work with them somehow, basically no matter what you're trying to do. So we'll start with geometry. So if we want to do 3D graphics, we have to have some sort of 3D objects that we want to draw, and that we want to model. So somehow we have to describe the 3D things that we want to view, and typically we use meshes for this. Okay. So a mesh is a collection of simple primitives, which could be either triangles are probably the most common. For some applications, it's common to use quadrilaterals. For some applications, we can actually use functions. So if I wanted to draw a sphere, the way I might represent my geometry is I have a function, and my object is wherever this function equals 0, which sounds kind of weird, but that can actually be useful and very efficient. And there are other ways that we might talk about our geometry, but these are kind of basics. So triangles are nice because they are the simplest way of representing a surface in terms of like the number of vertices. Triangles are always flat, which is a very convenient thing. Quads are not necessarily flat. In fact, in general, they're not flat. And they might not even be convex. So we can have all sorts of weird stuff happen with quads. So even in 2D, you can get weird stuff like this. So this shape is not convex. I think in the security class, somebody gave a this was your presentation about the concavity check. So this being concave causes a lot of problems because I would kind of like to just be able to draw around the boundary of all the points that I have, right? And just like fill in everything inside there, and that doesn't work because it's concave. If I'm in 3D, I have a quad. I can have two vertices, these two vertices high, these two vertices below, and I get this weird twisted thing. So again, triangles are really nice because they don't do that, they're always flat. Quads are useful because you can line up the edges to have nice directions. So they get used a lot for modeling, and actually for modeling stuff you kind of don't want flat, right? You want to have nice like organic shapes with curves and stuff. So they're harder to draw, but they are often more convenient for modeling. So for a lot of applications, we at least start with quads. So that's kind of a common representation. It's easier to take quads and get triangles than it is to go the other way. So quad meshing, taking a shape and making a representation of the surface that only uses quads, is actually really hard. It's like still an active research area, whereas turning any shape into triangles is really easy. So, and then these types of representations, the implicit representations, when they work, they're super awesome. So how many of y'all have seen Tron? Like the original 1982 Tron? The light cycles are, the geometry is something called constructive solid geometry. And what they do is they take these implicit function shapes. So these are objects where there's like a really simple mathematical description, like a sphere. So anybody know what function I would use to describe a sphere this way? That's the volume. So I want to take a point, I want to plug in some point in all of space, and I want to get 0 when I'm on the surface of the sphere. So a little bit weird. So my f of x is just basically distance minus the radius, or position minus the radius. And when I'm on the surface of the sphere, this function will be 0. When I'm inside the sphere, it'll be negative, and when I'm outside, it'll be positive. Okay. So this is an infinitely precise sphere. There's not going to be any like sharp edges or anything. This is like a perfect sphere, and I'm describing it with, So I guess the real way I'd write it is as a vector, like x minus the center.
You just square root it.
I put a squared on the radius. Square roots are slow, squares are fast. So this is how I really represent it. I just need to say where the center is, what the radius is, and then I can evaluate this function at any point. And if it's 0, I'm on the surface, and I should draw there, and if it's not, then I won't. And for some rendering techniques, this is really efficient. So Tron, basically all of the light cycles, they take these simple shapes and they add and subtract them. So they basically say, they do like Boolean operations. So, the light cycle, the yellow part of the fender is inside of the circle and outside of the cylinder, and so that's how they specified it. So there's no like meshes or anything for the light cycles, which is pretty cool. So you can do these implicit representations are pretty powerful. Those are kind of cool. Yeah.
What was it doing using polygonal levels?
For modeling, they're kind of nice. For rendering, they're not so nice, but for modeling, they're pretty nice.
What?
So there's going to be fewer of them. The fact that there's 2 directions means you can do some alignment stuff. Right? If you try to have triangles that like are in strips that are like perpendicular, it's really hard. But you can do that easily with quads. Sometimes you want the fact that they're not flat. So if you wanted to draw a smooth surface, it's harder to render, but you like the sphere, you can describe sort of infinitely smooth things with the quads, with the triangles you can't.
Feels like if you make triangles small enough, you get something.
So you can totally do that, but you might have to, knowing how much to subdivide can be tricky. Like doing the subdivision to cut the quads into triangles can be tricky. So if your renderer can deal with these directly, then sometimes they're nice to work with. Yeah, so that's geometry. So we'll talk a little bit about how we store a triangle mesh. So what's how would you approach, you have an object that's described by a whole bunch of triangles. What data would you store to represent that?
We should just store the points of every triangle.
So how many, so I'd have like one gigantic array?
One and I usually say yes, but I feel like an adjacency matrix one would too.
We'll talk about that in a sec. That's kind of an optimization. So if I just stored the points for every triangle, how many? Let's say I have floats. Right? How many floats are going to be in my array?
3n.
Where n is the number of
Triangles.
So for each, so 3 being the number of points, right? And then n being the number of triangles. I actually need a few more floats than that. Because for each point, how many floats am I going to need? 3, right? So I need x, y, z for a, b, c on every triangle. All right, so if I store my triangle mesh as just one big long array of floats, right, I have 3 times 3 times, I call this t, the number of triangles. Okay. So this could be pretty big. And there's actually a whole lot of redundant information in here. What, anybody?
Triangles intersect.
Well, hopefully they don't.
Well, I mean, like the points.
Hopefully they intersect in a very controlled way.
Right.
But the points are definitely reused, right? And on average, if you have a closed surface, I think they're reused 6 times on the average thing. So the average degree of each vertex is 6. So I'm storing 6 times as many points as I probably need to do. So we're actually going to do something like a little suggestion. The typical approach is to break this into 2 array. We have a vertex array where we just store the positions of each vertex. Right, so this is going to be 3 times v floats, where that's going to be way smaller. Right, and then the index array is I just store 3 ints that point into this array for each triangle. Okay. So if a float and an int are the same size, I cut down my storage by basically a factor of 3, right? Because for each index, instead of storing 3 coordinates for the point, I store 1 index. So that's pretty handy. And then very often, you actually don't have to use ints here. If your object isn't that big, you can use a smaller index type. So you could use 32-bit floats over here and 6-bit or 16-bit ints over here, unless you have enormous mesh. So this is the optimization we use to store stuff. We usually have just an array with all the vertices, and then we just index into it for the triangles. So yeah, this is how we typically represent 3D geometry. Triangle mesh is kind of the most common and simple and basic, and this is the typical way that we would store that data. Questions on geometry?
Describe the vertex index interaction again. I don't think I followed.
So I basically just number each one of my vertices, and then to store a triangle, I just say this triangle is made up of vertexes 7, 20, and 13. Okay. Yeah. So that's geometry. That's how I describe my objects. The next really important thing is transformations. So I want to, so if I have something animated, I need to move objects through the scene. But even if I'm just if I'm just modeling, I probably want to manipulate the objects to make things more convenient for me as the modeler, and potentially to save storage. So imagine you're rendering, you want to draw a forest. You could specify every single triangle of every single tree, but that's going to be a lot of memory used for storing trees. So how could we, cheat and get away with using less storage?
Store one and store this change that happens. So whether it's a size change or what you want to do to the one.
Yeah, I could use the same tree geometry and then just put it different places, maybe change the size or do other transformations to it. But I want to reuse the same geometry, but I want to transform it different ways. Okay. So there, yep.
When you're doing visualization, how often is the computational limiting factor, how often is storage limiting factor? Like if you're doing this, you're saving a lot on storage, you have to do a lot of math, kind of just change.
You have to do very little math.
Really?
So the transformation, so we're doing a forest. Transformations we might do are scale and translate.
But you have to do it for every single point, right?
For every vertex, yep.
That's
So that is true. However, we are going to be transforming every vertex already, and we'll talk about why. So we're already doing transforms. And we can basically combine, so applying a transform is basically multiplying by a 4x4 matrix. We can combine transforms. So I can do 100 transforms. And all I'm doing when I apply a bunch of transforms is changing what that matrix is. And at the end, I'm just multiplying every point by that 4x4 matrix. So it actually does not increase the computation cost in a significant way. Yeah, the computation is low. Also, the computation is the same for every point. It's multiply a point by a matrix. And that's a relatively simple computation to do, and it's like highly structured. So since the 90s, there's been specialized hardware that does it, which is the graphics card in your computer. So this stuff has been super optimized hardware, so it's almost free to do. So the computation cost is really low. Yeah, the transformations we might want to do is our translate. So we want to move stuff around. So if I have a point and I want to translate it, what operation do I have to do? I just want to add or subtract to it, which sounds like it's in opposition to what I just said, which is we multiply by a matrix, and you said add. Adding and multiplying are different things. So we'll talk about that in a second. So that's one translation. Other things I might want to do are scale. How do I scale stuff? Just multiply. And then the final sort of fundamental operation is rotation, which is also a multiply by a special matrix. Let me draw these out. I can go a little deeper into math. How many of you have worked with matrix math in the past? A little bit.
That's a probably answer.
We'll start with scale because that's real easy. Right. So I have my point x, y, z. I have some scaling matrix here that I want to multiply by. We'll just do a uniform scale to start with, but you could scale the different dimensions differently if you wanted. All right, and the answer I want to get out is a new point with these values. Anybody remember enough linear algebra to remember what it gonna look like? So it turns out the scale is just, it's a diagonal matrix, and I just put my scaling vectors down the diagonal. I can kind of talk about my scale just using the one number s, but when I want to turn it into a matrix, I have to fill in more stuff. Rotations are a little bit trickier. There's sines and cosines. There's a bunch of different ways to represent them, but it's going to be a matrix. The tricky one is the translate. I want to add some values A, B, and C to translate it. As I've kind of written it out, this is actually impossible. Okay? And to understand why, imagine my point is at 0, 0, 0. There's nothing I can multiply by here that I'm going to get A over here. Right? I'm trying to multiply by 0, that just doesn't work. So we're going to make things easier by adding an extra dimension. So sounds crazy, but what we do is we just stick a 1 here in the 4th dimension. And now it's really easy. I just put my ABC here in the 4th column, and I basically, at the end, I say plus A plus B plus C, no matter what my X, Y, and Z are. So that's pretty cool. And then here I have, so this is the identity. I just put 1 down the diagonal, so nothing else changes. And so this is a translation matrix. And so the trick there is I add an extra dimension. And I add an extra 1 here. This is called the Homogeneous Coordinates, which basically is 1 if it's a normal object. But you can do cool stuff by, like, if you set it to 0, your object is like at infinity. So like if you wanted to have the sun in your scene be very far away, you can set it to 0, and then it's like unaffected by some of these transformations. So that's the trick, is I added an extra coordinate. For any of these other transformations, I just stick an extra row of zeros, put 1 in the bottom corner, and then it preserves this stuff.
What effect does this have? Is this shared space?
Yep, so this just adds ABC, so it just moves. It moves a point over. So these transformations, these are kind of the basics: scale, rotation, translate. And you can combine them by just multiplying the matrices. So to apply, a scale and then a rotate and then a translate, you just multiply those 3 matrices in the opposite order, and then you get this combined transformation that does all of those things. The order does matter, right? Translate and rotate. So the rotates are always kind of about the origin. So if you translate first and then rotate, you're going to get a really different thing than if you rotate first and then translate. So the order is important here. But
rotation is always done first in practice, though.
Usually what you do is you translate an object so that its center of mass is the origin, and then you rotate it, and then you translate it back. But it kind of depends what you're modeling. Right? If it's the solar system, you probably would just rotate about the sun or something. So you have choice in how you do this, but you can combine them basically however you want. All right. Yep.
So this is like pretty theoretical. If we were to try and a computation that's using 3D rendering, I imagine there are really specific libraries that you use.
Yeah, I mean, you'd say like, so OpenGL is an open source library. It's on its way out of its useful life, and what I'm about to say hasn't really applied to it for the last 5 or 10 years. But there's a function GL translate, that basically multiplies the current transformation matrix by a matrix that looks like this. So basically, these libraries, they make a 4x4 matrix and multiply it. And you just kind of store the current matrix. And then eventually you'll multiply all the points by it. But yeah, the APIs are just basically you specify which of these transforms you want. And we'll see a little bit of that. So the library we're going to play with today wraps some of that stuff up for you, so you don't. So there's some nice stuff on top of it, but
I guess it is like pretty consistently the way it's handled. It feels like if we're using some sort of nice API, we're not using anything in terms of matrices.
no, but you're thinking in terms of transforms. So rotations are another one. So like for the scale, we can store it more efficiently as one number than storing it as the matrix. Like sort of is an intermediate until we need the matrix at the end. For rotations, we can describe it with a rotation matrix. So we need kind of the 3x3 9-number representation. There's another way of representing rotation called the Quaternion, which is remember complex numbers. So Quaternion is what happens if you add 2 more types of like imaginary numbers. So you have an I, and a J, and a K. They're these really weird things, but they're a way of representing a rotation with 4 numbers, and they're super convenient to work with and really efficient for doing rotation stuff. So again, you might say rotation, and the library is doing Quaternion stuff, but you don't really care. Cool. So those are the basic transformations that we do for sort of modeling. We want to move stuff around and rotate it and all that kind of stuff. Next thing we'll talk about is cameras. So I have all this 3D geometry. I don't have any 3D displays, right? I have no way of putting the geometry in this room. There's a couple of like holographic kind of things, but nobody has those, and they're kind of weird. So really, I have to display my 3D world on a 2D screen. Okay? And so to do that, we're going to talk about cameras. The way that we're going to think about cameras is basically here we have the sensor or the film. And here we have the scene. That's my cool scene. And the way a camera works is it looks out into the scene, and basically I display whatever light hits the sensor. So geometrically, kind of looks like this. So I have, here is my viewpoint. Somewhere over here is the place that I'm looking. And then there's a couple other parameters that are involved with this, which are my field of view. So this angle here is my field of view. Okay. So usually, something like 45 or 60 degrees. If you wanted to do some crazy weird hyperbolic something or other, you could set your field of view to be greater than 180, right? So your camera somehow looks behind you. Right? I think there's like some games where you're playing as an alien, you have vision like that or something. But usually for like normal photorealistic stuff, this is, the related to my field of vision. And the other things, which are kind of more for, we're not going to explain why they're used. It's kind of a technical detail. But usually we have a front and back, near and far, called clipping planes. And so basically anything between my eye and the near clipping plane, I don't draw, I don't see it. and anything past the far clipping plane I also don't see. So there's, so here we'll call this a near plane, and the far plane, right? And everything in between those we look at, and everything else we don't. Cool.
Is the camera the function of the 3D model, or I figure the camera would be more like universal, so like you use the camera for multiple models?
Correct. So the camera is independent of the models that you have. So I have all this geometry and stuff. I can put the camera is independent of that. Like it's going to look at that geometry, but I could have, I could have multi-views of it. I could reuse the same camera setup for different models. They're kind of independent things, but I have to combine them together to get an image.
It feels like there would be a cheaper way to make things appear 3D since it's going to be 2D eventually anyway.
So model it in 2D directly
Right.
somehow.
But a lot harder, that sounds.
Yeah. We'll talk about why. So for shading, when we talk about shading, you need the 3D information. So yeah, this is kind of the model. Yeah.
Just real quick, reason why I asked my last question is because I've done a little bit of work on this in my personal stuff, but I'm very new to it, but from what I can tell, like some of the 3D modeling, some of the 3D model formats will take a camera parameter.
So that would be like a scene format.
Okay. What's the difference there?
So the scene would be like everything that you need to make an image. The model would be geometry, surface information, so what color is it texture information, all that sort of stuff.
Yeah.
And the scene would be like, these are all of the objects that are here, this is where the camera is positioned, this is this is where the lights are. So that stuff would be the scene. And so you need all of that to make like an image.
So is that sort of an optional parameter when you're building a 3D model?
So if you're just doing the model, right, if you're just working on the geometry, like the camera is useful for the modeling application, right? So if you're in Maya or whatever, like there's a camera in Maya that you're looking at the model that you're making, but that's not really, like that's just the editor.
It's sort of like it's a default, it needs something.
So the editor is also a renderer. So the editor has a scene with one model and a couple of simple lights and the camera that you're moving around as you model. But if you're going to stick it in a video game or a movie, it's going to be a different camera. Or the camera is going to be, the FPS perspective, or some shaky cam, J.J. Abrams, whatever. Every time we're looking at a 3D object on a 2D screen, there is a camera involved, but it's not associated with the model. It's associated with the scene or the application that you're working on.
Maybe this doesn't matter if I didn't understand that distinction at all, like between the scene.
So this, so if I'm making a movie, I need to set up my shots, right? So I need to create the geometry I want in there. I need to place it. I need to decide where I want to put my virtual camera, right? All that stuff. I need to put the lights around, all that stuff. So as I'm editing the scene, I'm usually doing that using a 3D view of the scene, in Maya or something, where I'm going around, taking my objects, I'm placing them, and changing my point of view, tweaking whatever. Right, so that is a scene, right? Because I'm getting a picture of, like my wire frames and all that, the low res, whatever. And then when I go to get my shot for the movie, I'm going to use a different camera that's, placed, with nice artistic angle, right? And then I'm going to get a picture from that camera as well. Okay. So for when I'm, usually those are two different use cases, right? There's the editor and the modeler, and then there's the end viewer and user, right? And each one of them will have a different camera.
How many cameras is the typical for the final scene?
Good question.
Like when you're actually just finishing it, is there most people use this many?
So, so if you're shooting like a normal movie, like a live action thing, you probably have what, like maybe 2 to 10, depending on what you're doing. And it's probably similar for animated thing, right? You're a director, you storyboard what you want to see, you figure out what angles you want. And the advantage of animated stuff is that if you don't get the shot you want, you can say, okay, well, what happens if we put the camera here and shoot it again? So that's like, it's easier to get a new angle. But I think for like a movie, probably ahead of time, they pick like, here's the whole shot that I want to see, so put a camera here. For like a video game, right, there's one camera.
So like for yours, when you did the like car smashing,
Mm-hmm.
did you like run it on over at like different angles? And
Uh,
then you remember them all?
Yeah, so what I did, so I had an interactive editor, so I looked at like a low-res version where I could move the camera, and then I picked an angle that looked good through the whole scene, and then I did a pretty render from that camera perspective. Yeah. I wouldn't use me as an example for how to do any of this stuff well, because I have no artistic ability or eye for this stuff, but yeah, that was my approach. So we have this camera, it's looking out into the scene. So this kind of tells us what region of space we're looking at, what should be in our field of view. But still we have to take that and we have to somehow get it onto 2D, right? This is still 3D, right? But we have to get it here. Okay. So the first thing we're going to do is we're going to apply transformations to transform this region of space into a 1 by 1 by 1 cube that is axis aligned, because that makes everything else easier. So what we're going to do is we're going to apply all the weird transformations. We're going to make some matrix that takes whatever this region of space is, and it transforms it into a cube where the z-axis goes this way, right, and then the x and y are these directions. So the x and y are like the film, and the z is the depth. Okay. And so this is like a weird transformation. It's not quite any of the ones we've talked about, right? But that's kind of the first step. And that's why the near and far planes are useful, is because we have to know where the front and the back of the cube are. Okay. And now we're ready to project everything we see in here onto our film. So the easiest thing we can do is what's called a orthographic projection, which is used sometimes for modeling. And what we do is we just take the depth information and we throw it away, and we just take the x and y coordinates of everything in here, and that's their x and y coordinates of the film. So we use the depth information for like sorting, so we don't draw things that are further away on top. But we just draw stuff basically front to back. We throw away their z coordinate. We ignore how far away they are from the camera. Okay. So this is dimensionality reduction using a very simple technique. We just throw away one of the coordinates, and that's it. So you don't see this technique used in a lot of movies or anything photorealistic. What do we lose by doing this? This is not how our eyes or a normal camera works.
Yeah, perception.
So we're throwing away the depth. What is the effect of depth when we're viewing stuff normally? So we can do shadows and all that stuff. What we're missing here is things that are farther away appears smaller in real life. Okay. So basically, the depth should be used to scale things that are further away from us. And that's what we're missing here if we use orthographic projection. So we throw in the depth information, we don't get that. So this marker here versus in the back of the room would appear the same size in an orthographic projection. So what we normally use is something called a perspective projection. How many of you have taken like a basic art class? So what is, you talk about perspective drawing? How does that work? So you have like viewpoint at the vanishing point, and so lines stay lines, right? Vertical stay vertical, horizontal I think stay horizontal, right? Diagonal things, head towards the vanishing point or whatever. That's the idea with perspective projection. The key like mathematical trick is that at some point we divide by the depth. That's kind of what's going on there. Normally what you do is perspective projection, where we use the depth information to make stuff that's further away smaller. So that's the whole process, right? We do modeling stuff to set up our scene, right? So usually there we work in what we call world coordinates or modeling coordinates. So you might set stuff up so your units are meters or whatever, just to kind of understand what things mean. Right? Then you place your camera and you fill in all these properties. So where is it? Where is it looking? How wide of an angle can it see? What is the range of its view? And then that whole sequence gives you a single matrix that takes the XYZ points of the models, transforms them as they're placed in the world, and as they're viewed by the camera, and the output that you get at the end is XY. So that's basically the whole process. We take our coordinates, our XYZ of the models, multiply them by a matrix, and we get pixel coordinates for what we see. Cool. So that's a camera. Again, these are the knobs that we get to play with. The near and far clipping planes. The near one actually is kind of finicky, which is obnoxious. The far one doesn't really matter. If you set the far to be really far away, you kind of lose a little bit of depth resolution. So if you set it really big, things that are close together, you might not get consistent, like which one is in front of the other, due to like numerical errors. The near clipping plane can cause problems if you set it to be too small. But that's how we get our 3D objects into our 2D film. So the last topic we'll talk about is what our geometry looks like. Okay? And so this is shading. So I have these objects, I know where they are, I know where they will appear. Now I need to know what color they should be. Okay? And this is why doing stuff in 2D is not really an option most of the time. Or one of the reasons. So there's a few different ways we can do shading. Right? Typically, when you're modeling an object, you will specify a color for the object for how it reacts to each of these different types of lighting. And then some of them are combined sometimes. And then the final image is you just add up the contributions for all the different types of lighting. Okay. So here's my object over here. The first type of lighting that we have is something that is completely non-physical. And this is called ambient light. Okay. And this is like background light that is everywhere all the time. And any object in the scene is illuminated the exact same way by this ambient light. Okay. Probably multiplied by the object's color. Okay. So the ambient light is a constant thing for all the objects. And so, yeah, there's no differentiation. If the object is visible from the camera, the ambient light is this color. Okay. The next type of lighting is what starts to make things look realistic. called diffuse lighting. Okay. This is for objects that are, or light that comes from objects being generally kind of rough at a microscopic level. And the idea here is that if I have some object and I have some light that hits it, basically the light scatters evenly in every direction. And so when the light hits here, I get light out evenly in all directions. Okay. So the position of the viewer doesn't really matter for how bright this is. Right? No matter where I put my camera, right, I'm going to get the same light out of this object. That kind of makes sense. The brightness does depend on the angle between the light and the surface. Okay. And so basically, the way the diffuse lighting is going to depend on the normal vector of the surface. So this is basically an arrow pointing out, perpendicular out of the surface. So here would be my normal vector. Okay, and it depends on the direction of the incoming light, but like flipped. So L would be, so here's my light bulb. That's terrible. My light bulb, my L vector is going to point from the point I'm shading to the light. And the diffuse depends on the dot product that we done. So if my surface is oriented pointing towards the light, it's going to be brighter. And if it's like perpendicular, it's going to be darker. So this is diffuse lighting. Also known as matte lighting. So if you see a car with like a matte paint job, that's how the shading works. It looks the same no matter what your view direction is, right? So if you move around the car, it looks the same. But if the car moves and the angles between the car and the light change, then the shading will look different. And then the last kind of lighting we'll talk about. One of the models of this was actually developed by a PhD student at the U in the 70s. It's called specular lighting. And this is mirror-like reflection. So if you look around at the tables, you'll see certain view angles, you'll get brighter highlights. It almost looks like a mirror. Whereas other angles, it looks kind of flat and diffuse. And the specular highlights are the kind of really shiny highlights that you get, where based on the angle of you and the light, the object is kind of working like a mirror. So the specular highlights, if we think of our object as kind of like a blurry sort of mirror, and we have a light over here. And this is the point we're looking at. So again, this is my L vector. Where do we expect? So first off, so if this is a mirror, does the brightness that I see looking at it depend on where I'm at? Yeah, it definitely does, right? If I'm somewhere over here, I'm not going to see it at all. If I am down here, right, I'm going to see the light. So the brightness for this, right, it's going to be brightest here, and then it's going to kind of fall off as I go away from this, right? So this direction, so this is my normal vector. The brightest direction is the one that's the perfect reflection, right? It's the same angle, but on the opposite side. And then as I get away from this angle, then I'm going to be, it's going to be dimmer. Okay. So we call this R for the reflected direction, And then put the camera here. Call this the B direction. The closer the B and the R directions are together, the brighter the specular is going to be. So the specular depends on B dot R. If those two directions are the same, it's going to be the brightest, and then it falls off pretty quickly. So this is usually something that looks like B dot R raised to some power, where the bigger the power, the faster the fall off. So if you set this R to be like 100, it's going to be really mirror-like. It's only going to be bright in this tiny little region around it. If you decrease that exponent, it'll kind of spread out, and you'll get the highlights in a wider area. So these are kind of the three fundamental lighting contributions. There's a ton of research on accurate models of the interaction between lights and surfaces that describes exactly how light scatters, that conserves energy and does all sorts of other stuff. But these are just kind of the basic, simple 3D graphics models.
Are there certain properties of the model that affects this, or this is more of a scene?
What matters from the model is the normal direction. So that's something that the model needs to provide. So a couple ways you can do that. I would say the sort of simplest good way is so for any face, for any triangle, you can compute the normal direction easily. We'll look at how to do that. For a vertex, it's kind of weird because you have a bunch of triangles that intersect that are facing different directions. So if I wanted to figure out what the normal was at a vertex, what do you suppose I would do? So I'll draw a 2D example. So here, the normal for that triangle is this way, the normal for that triangle is this way. What normal direction makes sense at this point where they meet?
So say it's just the x coordinate from their intersection.
Well, so it's hard for me to, if I didn't know what else was here, basically there's no way I could pick what it should be. But since I know I'm touching these other two faces, I can use that information to pick something reasonable. So kind of the easiest thing I do is just average the normals of all the things that touch at that vertex. So in this case, I would just take these two, average them together, and maybe I get that. So typically, I take my geometry, I compute what the normals should be at every vertex, and then that gets used as part of the contribution to the shading. But that's really the only geometric thing. The other thing that's kind of related to the geometry is these properties can vary across the surface, which we call texturing. So I have, right, so for the shirt, I don't need to put a whole bunch of triangles here and have each triangle be a slightly different color around this line. I really want to just say, hey, there's a pattern that goes across the surface, right, and use fewer triangles and then just provide the pattern, as well as how to put the pattern on my triangles. So that's called texturing. So the geometry also usually has what are called texture coordinates. So if I imagine my pattern is like a sheet, like printed out, the texture coordinates say basically where in the sheet should I get my colors or other properties from. So that's kind of the other modeling thing is providing texturing or texture coordinates. Cool. So that's shading, right? You can get crazy complicated. and really physically accurate with that. But it relies on this 3D information of the relative directions of the lights from the viewer and the normal. Cool. All right, so we're going to look at some sample code in a little bit. So we're going to look at just a really simple, like 10-line demo, just to kind of play with this stuff. And then we're going to look at a more complicated data viz problem. And we're going to sort of talk about our strategy for that first. Okay. So the data set that I have is elevation data for the 1 degree square region surrounding Salt Lake from the USGS. So basically what I have is this big grid, and at each point I have the elevation, and this is just stored as a big matrix. It's just a big, just long array of floats where each float is the elevation of a particular point. The coordinates are not stored in here. It's just, they're just stored in order so that they go through this. And I want to visualize this data with some cool 3D graphics. Okay. I could use a color map, or I could use like the contour plot type stuff that we've done and do 2D color map. But this is elevation data. I want to see it in 3D, right? I want to see the mountains. I want to see all that stuff. Okay. So somehow I have to turn this into something that I can stick in my 3D scene and draw. Any thoughts on how we're going to transform this 2D grid of data into some geometry that I can look at?
You probably want to start out with your viewpoint being like a bird's eye view.
So we'll talk about, so the view we're actually going to move around, but I need to, so the first thing I need is geometry. So I need somehow to turn this grid of numbers into some 3D geometry that I can look at.
So you from the cloud, you get all of your 3D points.
So the first thing I want to do is turn these into 3D points. Right, so right now I have like just the Z coordinate, or just the Y coordinate, depending, so just the up coordinate. Right, so I need to assign an X and a Z or whatever to each one of these points. Cool. So now I can transform this into a big old array of X, Y, Z points for each one of these elevation samples that I have. Cool. And then what geometry can I draw?
Just the points.
So I could just draw the points.
So like a contour.
So I'd like to draw the surface, right? So right now I have just points. I could draw these as little dots, and I could see like dots with space in between. But I want the surface. I want to draw I want it to look like I'm looking out of a plane or something.
So you can connect all the adjacent points of triangles.
Oh, so I want to convert this into a triangle mesh somehow. So let's look at just a tiny region. So this data is structured so that all of my points are, there are points on a grid. The XY part of it, or the horizontal part, is they're positioned on a grid. So that's kind of nice. So it's laid out like this. And I know the elevation, right? So these are coming out of the board, but I can't draw that. All right. And so somehow I want to turn this into triangles. So how can I do that?
I want to say just connect the point to the two closest points.
Okay, well that's part of the triangle.
Or, sorry, and then connect the final.
Cool. So do I want to do it like I could do? So this, I could take my quad and make two triangles out of it. This is not, in general, a very good approach. It's the approach we're going to take. But in general, it's not very good. Anybody see spot problems with this? So this is a biased way of cutting stuff up because I'm putting my diagonals facing the same direction. And that probably doesn't necessarily align with the data, right? If my point kind of had a valley this way, right? This is cutting across it. And so in general, we'd want to be smarter about exactly how we do this, but we're not going to. And so we're just going to take our data, turn it into 3 points, connect each little 2x2 patch into 2 triangles, and then now we have our geometry, and we can pick whatever surface material we want for it, and put our lights and our cameras and all that stuff. I didn't really talk about lights at all, but we just put them in the scene. There's different kinds of lights. So there's point lights that shine the same brightness everywhere. There's spotlights where there's a directional component that's brighter in some directions than others. There's other kinds of lights, but yeah. Let's go ahead and take a look at a couple of examples. So the library we're going to use is called 3JS, which is a JavaScript library. It uses a WebGL, which is basically a browser API for OpenGL, which is the most common, or say the most common, the only open source sort of graphics API. Cross-platform, runs a lot of places. Yeah.
So earlier you said that OpenGL was kind of out. What's in there?
So OpenGL, the API is kind of high level, and that means the drivers, the things that take the API and turn it into assembly language for your GPU, are really complicated and really crappy. So graphics card drivers, like for those high-level APIs, just suck. And so the newer APIs would be Vulkan and Metal and DirectX 12, or I think the latest one. And those are much lower level, where it's a lot closer to the graphics card assembly language. And so it's a pain to program, but you can manage the threading, and you are responsible for correctness, as opposed to NVIDIA or AMD. On embedded devices, or like phones and stuff, I think mostly people still use OpenGL ES, which is like a stripped down. They threw away a bunch of the old crap, but it's still a relatively high level. I don't know if Vulkan is popular on like Android yet or not. Metal is Apple's. So there's a group called Kronos that's like a nonprofit group that is responsible for OpenGL and Vulkan. And so NVIDIA and Microsoft and Google and Apple and AMD and all those people are part of the Kronos group. And so they define the OpenGL API and the Vulkan API and this stuff. And despite Apple being on this committee, they have said that they will not support Vulkan on any of their OSs. So you're stuck with Metal or OpenGL on Apple stuff. So yeah, that's kind of where we're at. But Vulkan is kind of the next thing.
Is that if it's a browser? Would that be a browser?
So what happens is when I do WebGL, Chrome just takes the WebGL commands, converts them into OpenGL commands, and runs them and displays it. So this is the first thing we'll look at. We have this beautiful dodecahedron geometry that's spinning. Right? So you can see the, I don't think there's any specular highlights on here. You can see the diffuse shading. So when the faces are pointing in this direction, they're brighter because there's a light over there, right? And when they face toward the light, that's when the diffuse lighting is going to be brightest, right? If I wanted to do specular highlights, I would have to position the viewer kind of close to where the highlights are, or close to where the light is, or the angle. I would have to be in the reflection direction of the dodecahedron to see it. So let's take a look at the code that's involved here. So we'll just look at the HTML. Basically what we're going to do is we're going to have a canvas element, which is what the WebGL is going to draw on. I guess that's okay. And then let's look at what's in here. So I have a scene object, so this is going to store my models, my lights, my whatever materials I attach to the models, my camera, all that stuff is in the scene. I'm going to have a perspective camera. So this is a 75-degree angle field of view. So let's take a look at this again. So if I wanted to zoom in on this object, I can actually do that by changing the field of view. So how can I do that? Should I increase it or decrease it?
Would you decrease it?
If I decrease it, right, my object is going to fill up more of my field of view, and so it's going to be bigger. So let's shrink that down to 45. And indeed, it does get bigger. So this is kind of a weird way of doing zooming because it doesn't really correspond to anything that like people can do. And even cameras, this isn't really how a camera zoom works either. So this is kind of a weird thing. Usually you don't mess with the field of view, but you can, and it makes it bigger or smaller. So cool. We have that. Here's our aspect ratio. Oh, sorry. So this is the field of view, which says how wide our camera's open. Then we have this other thing with the aspect ratio. It didn't make sense on the board because it was in 2D, but in 3D we actually have to specify basically the height and the width of our film. And so the way we specify that is the field of view in the Y direction, and then the aspect ratio, which is just the ratio of the width to the height of our screen. So that's how it's specified for whatever reason. So this is just saying what shape is our screen. Here's my near clipping plane distance. So objects closer to the camera than 0.1 units won't get drawn, and objects that are further than 1,000 away won't get drawn. And then we're using WebGL. Here's where we get our canvas element that's all hooked up to do this stuff. So the 3JS library is doing something here to give me a nice canvas element with WebGL. And then I'm actually going to set up my scene. So my geometry is a dodecahedron. Okay. So this is the mesh made out of triangles. They are triangles even though they look like pentagons. They're sliced up into triangles. My material is a Fong material. So Fong is the guy that was a PhD student here. And he's the guy that came up with that clever representation for approximation for specular highlights. So the color here is purple. So I have red and blue all maxed out, which is weird because it appears kind of pink. Any ideas why that's happening? Is the shading, because the lights that I have are red lights for the most part. So it doesn't matter what color the material is, it matters how the material and the lights interact. So I don't have any blue light sources, or I don't have very many blue light sources, so we're not seeing, it would reflect blue light towards me, but there's not any blue light, or there's not much blue light to reflect. So, yep. And cool, so now I'm making my object, which is a combination of geometry and the material. And so now this is the thing I can draw. I put it in my scene. And I'm not applying any transform, so I think by default it's at the origin. So it's at 0, 0, 0. Adding some lights, I have a spotlight. So the spotlight has a directional element to it. I think it points down, so I'm putting it above stuff. So this is a red spotlight, so it's only going to shine, it's only going to color stuff red. And then I have a white spotlight somewhere else. I'm moving the camera back away from from the scene. And then here's the render loop. So this is what's happening each frame. So this request animation frame says basically when the browser is ready to draw something else, it'll call this function. Right now, since the browser is not visible, it's not calling this ever. So this is like a good CPU saver. If I use like set timeout, it would keep happening even though I can't draw anything or I can't see anything. So, request animation frame it's a relatively new JavaScript thing. It's pretty nice. And then here I'm changing the rotation slightly. So the transformation for the cube is changing a little bit every frame, which is why it's rotating. I'm calling this a cube even though it's a dodecahedron. And then this is where when it actually draws, this is going to call all the OpenGL stuff to draw all the models and stuff. Cool. So there we have it. Pretty basic scene. This is a kind of a tricky thing to get started with, because if you get stuff wrong, you just see a black screen. And so there's a whole bunch of things that could be wrong. Your camera could be pointed in the wrong way. Your object could be not where you want it. Your lights could be not what you expect. There's a whole bunch of things that could be going wrong, and figuring out which one of those you screwed up is going to be a big pain. So some tricks would be like crank up the ambient light really high so you can see objects even if they're shaded incorrectly. You can find them. You know, double check where your camera's pointed, all that sort of stuff. So that's some debugging tricks there. Okay. All right, so the next thing we're going to look at is the elevation data. So maybe I'll just start by showing you what that looks like. This takes a little while to load because the elevation data is a big file, but it is the USGS elevation data for this region of the US. And does anybody recognize it? So what's this here? That's the point of the mountain. We are sort of here. Let's see. Point of the mountain. I think we're like here, right there. So this is probably Parley's there. So what this is a rendering. This is a wireframe rendering. So if we zoom in, we'll see that the triangles are black with just the edges drawn. So this is a non-realistic shading. Right? This is I don't know, the visualization shading. But the material I'm using, it draws nothing in the interior, it just draws lines. It just draws a solid color on the edges. There's no lighting, I don't think. So yeah, it's the same purple everywhere. Right? Things just look brighter over here just because there's more purple lines and less black. Cool. So this is what we have to work with. So let's take a look at how we did it. So again, we have a scene, we have a camera, same deal. So this time my units are a little bit different because the scale of stuff. So my close clipping plane is 100 units away, and I think my modeling units here are meters. I'm going to change the camera target and position over time, and I'm going to be looking at different parts of this scene and moving the camera around. So the render stuff, that's the same. I'm loading my file, this file here, using this 3JS file loader thing. So let's just take a look at it. So this is the file. I'm just going to open up in a hex editor. And all it is just a bunch of floats. So if I select this and look at it as a little endian float, see the elevation here is 1,281 meters, right? So it's just the elevation in meters at every point in this region. And so this is a nice format for me. I don't have to parse anything, right? It's in exactly. I can just copy this file to memory and I have my floats, so that's pretty nice. Cool. So then I get my data. I'm going to make this float 32 array. So JavaScript is kind of a weird language to do with this because it's weakly, weirdly typed. So there's these like array types that give you more efficient like packed data storage stuff. So the next thing we're going to do is take these elevations and convert them to 3D points. So I need to figure out basically where they are in terms of x and z. So what my, the x and z coordinates in meters to go along with my y coordinate in meters. So all this stuff here is basically converting the latitude and longitude to a meter, to a meters representation. So that's what all this stuff is. This, I don't remember where this formula came from, but it's you can figure out the number of meters per degree latitude at different points in the Earth. So that's about, and then this function here is helpful. It takes an array of vertices and it adds a vertex. So it takes the x and z positions from, those are like the horizontal positions, and then the y is the elevation at that point. So, all right. So here, this is where I'm making the two triangles. So I have the top left portion and the bottom right portion of my quad. I'm splitting it diagonally. So I'm just taking the three vertices here. And I think here I'm actually using, I'm being dumb. I don't think I'm using indexing here. I think I'm actually just duplicating the vertex information. And this downsampling, the data is way more precise than I want it. So I'm actually throwing away, I'm only keeping like 1% of the data points to draw. Because I think it's every 3 meters I get an elevation point, which is way more precise than we want to see. Right, so we have the vertices here. The ordering here actually really matters because of the way that we compute normal vectors. So usually the way you compute normal vectors is you take two edges of the triangle, and you take a cross product, which gives you a perpendicular vector, but it could be in or out depending on how you order the points. So we want to order stuff so that if you go around the points clockwise, you point out of the object. So we have to be careful to make sure that we orient the points correctly. That's called the winding. So here I was careful to do that. The normals here, we're going to compute the normals for every vertex so that we can do some shading when we change the material to actually be shaded. And so basically the way we do that is we get the vectors along the edges of the triangle, and then we take a cross product, and that gives us the normal direction. This part here is where we're creating the geometry. So we're basically taking these arrays of vertices and arrays of normals and sending them to the GPU. So this is doing some sort of OpenGL stuff to copy this data to the GPU, except on this particular processor, it's not doing any copying because they share, it's an onboard GPU, but whatever. Here I'm using a Lambertian material, so this is a math material or a diffuse material. So there's no specular highlights. And then I'm putting my material and my geometry together to get a mesh. This wireframe geometry is just going to give me the edges, so that's where that came from. And let's go ahead and we'll change this to use this Lambertian material instead. My camera, I'm going to point at the middle of the data. So I'm going to point it above the center of my elevation data. I have a couple of lights overhead. This is a handy thing in 3JS, light helper. So this is actually going to draw a little circle where the light is so I can see it. That's another thing you can screw up is you're like, everything's dark and it's because your light's in the wrong place. So that's kind of a helpful thing. I'm doing zooming. And the way I'm doing that is when I scroll the mouse, I'm moving the camera closer to what it's looking at. So I'm taking the vector from the camera to its target, and I'm moving in that direction or backwards in that direction to zoom in and out. That's kind of a more reliable and normal thing than changing the field of view. Okay. And then to do the camera can move around. The way I'm doing that is I'm changing the camera position based on the mouse movement. So I'm figuring out which direction I'm facing, which way is right and which way is up. And then I'm moving a little bit in the right direction based on how far the mouse dragged right, and a little bit in the up direction based on how far the mouse dragged up. And then, again, moving the camera position based on that. So that's what's going on here. And if we look at the surface rendered version, again, really ugly color choices, but nope, that's not right. The Python web server that I use, I guess, really aggressive about including cache headers. So it says, oh, hey, these files aren't going to change for a while, and then they change. The browser gets confused. So here we go. So we have an ambient light, which is why everything is a little bit gray. Then we have this yellow light here, which is my point light. As I scroll, right, I'm zooming in and out. I'm moving my camera forward and back. As I click and drag, I'm rotating it around the middle, so I'm moving it. If you look in here close, you can see the triangulation. You can see here, like I had a quad that I split the edge, and it gave me kind of a weird crease based on because of the quads aren't flat. Okay. And there you have it. So that's just a quick tour of 3D graphics rendering stuff. Key pieces: geometry, triangle mesh is the most common. Transformations: how do we move stuff around and basically position it so that it's displayed in the camera. We have cameras, which control what we can see and how we take the 3D stuff and stick it on a 2D piece of film. And then we have shading, which controls basically what color stuff is once it appears. Any questions about that? How many people are inspired to play around with all sorts of 3D stuff? It's pretty cool. It's a pain, but it's cool when you get stuff working. If you're interested in stuff, there's a former professor here that has a series of books that are now freely available called Ray Tracer in a Weekend. And ray tracing is another way of rendering, of drawing stuff like this. And it's pretty well written, and you get this cool picture out in the end. So fun to play around. It doesn't use the graphics card or OpenGL. It's a CPU-based thing, but you get really cool results with not a lot of code.
So is this not ray tracing?
This is not ray tracing. So radiosity, nobody really uses anymore.
Oh.
This is a rasterization. So they chop up the geometry and look at which pixels it overlaps with, and then shade those. So ray tracing, you would shoot a camera from your eye through the or shoot a ray from your eye through the pixel and see what it hits, and then kind of shade based on what you hit. Rasterization takes the objects, figures out what pixels they belong to, and then draws them.
Is it, I've heard that ray tracing is a little bit more computationally expensive.
Yeah. So I would say the bigger difference is how accurate you want your shading to be. And ray tracing allows you to do like really complex shading, which can be pretty strong. All right, cool. Well, I will see you all tomorrow. And yeah, good luck on Maroon's test.